Okay, this is the example problem number 2 on the stiffness method. This is exactly the same problem, number 1, we solved earlier, but we have made now some changes. For example, we have applied a rotation. Now there is a rotation of 0.002 radians applied at this support at A. In other words, this fixed support at A, it rotates clockwise by a magnitude of 0.002 radians. Whereas this support at B, it settles down by an amount of 1 inch. So now, how we can incorporate the effects due to this rotation and this translation in our analysis. Now we will be looking at this in quite detail in this problem. So the question is again to analyze this given beam using the stiffness method. The loading is exactly the same as in the problem number 1. We have a 2 kip per foot uniformly distributed load over this span of 15 feet, and we have a 10 kip load applied at the center of this span of total 20 feet. The EI values are given here for this problem. E is equal to the modulus of elasticity. It is equal to 30,000 ksi for this problem, whereas the moment of inertia is equal to 800 inch raised to the power 4. So when you multiply these two values and convert them into kip fit sphere units, we get this value. So we will be using now this value for EI in this coming steps. The next step is exactly as we did, is the same as we did in the problem number 1. What we need to do is to replace this joint by a fixed joint so that the displacement is restrained. So now we need to first specify the displacements. So we have specified the displacement at this joint B by this D1. Also, this hinge support is replaced by a fixed support. So now I got a restrained structure, okay, in which the displacement, the specified displacements are now restrained, and now there is no displacement possible at this support or at this support. Now, what are the values of this V1 and V2? So we need to find the values of V1 and V2. They are unknown. And what are the values of AD1 and AD2, which are the values of the actions corresponding to the specified displacements. So there is no external action present here. Also, there is no external action present here. So the AD1 and AD2 values are equal to 0. Okay, the AD values, which are the actions corresponding to displacements. So there is no external action applied at this support. There is no external action applied at this support. So the AD1 and AD2 value both are equal to 0. For example, if we have an external moment applied at this support, for example, we are told that there is a moment of, let's say, some magnitude, let's say of 4 kip fit applied at this support B, external moment. So then we are going to take this value of 4 kip fit as the AD1 value. Okay. Similarly, if we have any externally applied moment at this support, so we are then supposed to take that as the AD2 value. But in this problem, we are not given any such moments at these supports. So the AD1 and AD2 values will be 0 in this case. Okay, so we are done with the AD values, AD1 and AD2. So now this is our restraint structure. This is our restraint structure. How we get this structure? So we have restrained these supports. Okay, we have restrained the displacements at these supports. So by restraining those specified displacements, we got this restraint structure. Now, we need to find the values of the Areal matrix, and there are now some changes in finding the values of the Areal matrix in this problem, because we know that we have a total of 3 types of loadings applied here. The first type of loading is this 2 kip per foot uniformly distributed and this 10 kip point load. This is the first type of load, which is acting on these members. The second type of load is in terms of displacements. So now we know that we have a rotation of 0.002 radians here at this support, and also we have a settlement of 1 inch at this support. So it means that in a similar way as this 2 kip per foot load and this 10 kip load, as it is applying some effects on our structure, it is causing movements, it is causing shear in our structure. So the 0.002 radians rotation at this support, it also induces moments in our structure. So as we know that the Areal matrix are the values of the fixed end actions, and these fixed end actions should correspond to the locations of the specified displacements when the restrained structure is subjected to the actually applied load. So now actual applied load consists of this 2 kip per foot uniformly distributed load and this 10 kip load. Also, it consists of the 0.002 radians rotation at this joint, and also it consists of 1 inch settlement at this support. So now we need to incorporate the values coming from all these loading types. Okay, so now let's do this. In the step number A, we are going to find the values of Areal, which are coming from this 2 kip per foot and this 10 kip load. So I will be calling the values of the Areal matrix as the Areal dash values. Okay, so the Areal dash values. Okay, now let's do this. This is exactly as we did in the problem number 1. So what we do here, we find out these fixed end actions. Now in this plane, this 2 kip per foot uniformly distributed load is acting. So now from this, the fixed end actions are coming as WS square over 12 at both these ends, and the vertical reactions there to be equal to WL over 2. So when you find out the values, it comes out to be 37.5 kip fit, this 37.5 kip fit, and these are equal to 15 kips. Okay, so now in the second spin, there is a point load acting, due to which the fixed end actions, the moments, they will be equal to PL over 8. So this becomes 10 into the span, which is 20 times 8, this becomes 25 kip fit, and also these reactions are equal to P divided by 2. So we get them equal to 5 kip. Okay, So now what are the values of the Areal dash? We know that the Areal dash values are the values of the fixed end actions corresponding to the specified displacement. So we know that our first specified displacement is at our support B, and it is a clockwise, and we call it D1, you remember. So now corresponding to this D1, now we will be taking the values from these supports. So corresponding to this D1, we have this fixed end moment, which is 37.5 kPa, and this is clockwise. Our assumed direction of D1 is also clockwise, so this will be taken as positive. And this 25 kPa fixed end moment is anti-clockwise, but the direction of our assumed D1 is clockwise, so this will be taken as negative. This 25 kPa will be taken as negative. So now when you add them, you get 12.5 kPa as the value of Areal dash 1 or Areal 1 dash. Okay. So now what is the Areal 2 dash value? The Areal 2 dash value is corresponding to the next specified displacement. So the next specified displacement is D2, and it is, if you remember, we have specified it here at this support, and it was assumed to be clockwise. So now if you see this moment is also clockwise, and its value is 25 kPa. So now we will be taking this as the value of our Areal 2 dash. Positive. Why positive? Because it is in the same direction as the assumed direction of T2. So now this becomes the values of the Areal 1 dash and Areal 2 dash. So in short, we call it the Areal dash matrix. And what is the Areal dash matrix? It is now it corresponds to the values of the fixed end actions coming from the this 2 kip per foot uniformly distributed load and 10 kip point load acting on the structure. Okay, which structure? The restrained structure. Okay, so now we apply in the second part of this step 2. We now apply the this clockwise rotation at the support, and then we see that what are the moments induced by this rotation in our structure, and then we are going to take these fixed end moments corresponding to our specified displacements as our Areal 1 double dash value and as our Areal 2 double dash value. Okay, so what is the Areal 1 double dash value? It will be the value of the fixed end moment, which corresponds to the location of our specified displacement, which is D1, and this fixed end action should come from this 0.002 radians clockwise rotation. So when you rotate this this support, now it induces moment in this structure, and the values of these moments are equal to 4EI times this rotation divided by the span length, which is L. So at the near end, okay, at the near end, and at the far end, it is equal to 2EI times this rotation divided by L. And then to balance these induced moments, we have these vertical reactions. So the values of each of them are equal to 6EI times this rotation divided by L square. So as now we have restrained this support, so there is no moment induced beyond this point. So in this span, there is no moment induced due to this 0.002 radians clockwise rotation. Now we need to find out these values. So this moment, this induced moment, it is equal to 4 value of EI. This is the value of theta, which is 0.002 radians. This is the span length, which is 15 feet. So we get 88.88. Also, this value, as this is 2EI theta over L, so we get 44.44. This value is 6EI theta over L square, which is 8.88. And this is also 6 times this EI times theta divided by L square, so it also becomes 8.88. Now, what are the values of Areal 1 double dash? The Areal 1 double dash value is corresponding to D1. So this is our D1. So here we have this induced moment only, which is clockwise. So we will be taking it as positive. So we take this as 44.44 positive. What is the Areal 2 value? The Areal 2 double dash value is corresponding to D2. So as there is no induced moment at this support, so we will be taking this as 0. So this is the step number B. Now in the step number C, we are going to take the values of the fixed inductions which are induced due to this 1-inch settlement at support B. Values of the moment at the near and at the far end, they are equal to 6 EI times this settlement divided by the square of the length. And these reactions are equal times this settlement divided by L cube. So if you find out the values, these induced moments are equal to 368.88, and the vertical reactions, they are equal to 49.18. You know now the direction. We have explained it quite in detail in the last problem. So now the Areal 1 3 times dash. Now, okay, we have, this is just a name. You can give it any other name also, or you can use this also. So now this value will be corresponding to the specified displacement D1. Now, if you look at this structure, we have this 368.88 and this 207.5. These both these values are corresponding to D1, but our D1 is clockwise, and this value is anti-clockwise. This is clockwise, but this is anti-clockwise. So we will be taking this 368.88 as negative, and this 207.5 as positive. So when you find out minus 368.88 plus 207.5, you get minus 161.38. Okay, so this is the value corresponding to the D1. Now corresponding to the D2, the value is Areal 2 3 times dash, and we get the value as 207.5, this value. Okay, this is this value. So now we are done with this matrix also. So now we need to combine all these values to get the values of our Areal matrix. So now Areal 1, Areal 2, Areal 1 this single dash, Areal 1 this 2 times dash, Areal 1 3 times dash. Now when you add them, you get this minus 104.44. Similarly, if you add the Areal 2 dash and this Areal 2 double dash and Areal 2 3 times dash, if you add them, you get this 232.5 value. So now this matrix is now our Areal matrix. So if you remember from the last problem, we had only in the last problem, if you remember, we had only this uniform distributed load and this 10K point load. That's why these values were our Areal values directly. But now, as in this problem, we have this 0.002 radians clockwise rotation and this 1-inch settlement also. So that's why we need now to incorporate the moments induced by these settlements and by these rotations as in our Areal matrix. Okay, so now we have incorporated them in our Areal matrix. Okay, now the next step is exactly the same as we did in the previous problem. We have now to compute the stiffness matrix. How we compute this stiffness matrix? So we give a unit rotation. First, we give the unit rotation corresponding to D1. So our D1 is clockwise. So we give a unit rotation clockwise. Now, due to this clockwise rotation of unity, what are the induced moments in our structure? So now these are our induced moments. This 4ei theta over L at the near end, 2ei theta over L at the far end. Similarly here, 4ei theta over L at the near end, 2ei theta over L at the far end. Now to balance these induced moments, these are our reactions. Okay, we did explain this in detail in the last problem. So I don't think that I need to go in detail here. So because you already know all this. Okay, so now what we need to do here, we need to pick the values now of the S11 coefficient. What is the S11 coefficient? S11 is the value 8, 1, 8 coordinate 1 due to the displacement, or in other words, rotation applied at the coordinate 1, okay, S11. What is S21? The value 8 coordinate, the value of the fixed end moment or the fixed end action 8 coordinate 2, which is caused by the unit displacement 8 coordinate 1. So as you know that at the coordinate 1 we have applied the unit displacement, unit rotation. So now the values we are getting are the S1 and S21. So now we have to actually put this value of EI. We now have this value of EI. So when you put the value of EI here, you will get this value of S11. Similarly, we get S21 value equal to this one. And in the next step, now we have to apply a unit displacement, or in other words, a unit rotation at the coordinate number 2. Now, due to this rotation, the moments induced in our structure are 4 theta over L at the near end and 2 theta over L at the far end. Now, to balance these moments, we have these reactions equal to 6 theta over L square, 6 times this EI times this theta divided by L square. So now, what we need to do here is that we need to pick the values of our S12. Now, 12 means the fixed end moment, the fixed end value, fixed end this action 8 coordinate 1, which is caused by a unit displacement 8 coordinate 2. Now we have applied unit displacement 8.2, and we are picking the value 8 at coordinate 1, which is this value. Okay, it's 2EI theta over 20. Now when you put the value of EI in both these, we get now this value of S12 is equal to this one, and S22 equal to this one. So now this becomes our stiffness matrix. Now in the next step, we simply need to put all these matrices here in this equation. We developed this equation in detail in the very beginning of this lecture, lecture number 5. So now what values we have? We have this value. This is the stiffness matrix. And there is no EI with this because we have incorporated the value of EI in these values. Also, this 0, 0, they are the values of the AD1 and AD2. And these are the values of our ADL1 and ADL2. Now, I have shown this ADL matrix here also. The ADL1 value is negative and the ADL2 is positive. So this negative and negative, this will become positive. So if you solve these matrices, you get these values as the D1 and D2 values. Okay. Now these are our D1 and D2 values. Now we need to put these values here in this equation to find out the member end actions. Now these are our specified member end actions: AM1, AM2, AM3. AM2 is just to the left of this support. AM3 is just to the right of this support. Similarly, AM4 is here. AM5 is the moment. AM6, AM7 are also the moments. Okay, so now we need to find out the values of the AML, AMD. We already have the value of D. Okay, so now we need to find out AML and AMD. Now, what are the values of the AML? So the AML values are the fixed end actions. They are the fixed end actions, and these fixed end actions are corresponding to our these specified AM1 up to AM7 values. Now, corresponding to your AM1, you find out the value of the fixed end action, and you name it as AML1. But this AML1, as I have shown here, AML1 is corresponding to AM1. This AML1 value or this fixed end action, it should come from this 2 kip per foot load and this 10 kip load applied on your structure. Okay, so when you apply this 2 kip per foot and 10 kip load on your restrained structure, Now you need to find out the member inductions corresponding to your AM1, AM2, AM3, AM4, AM5, AM6, and AM7, and you call them AML1, AML2, AML3, AML4, AML5, AML6, and AML7. Okay, so now, as you know that the we have three types of loadings. One is this 2 kip per foot and this 10 kip load. The other loadings are in the form of displacements, which are the 0.002 radians and rotation and this 1-inch settlement. So we need now to incorporate the values of all these types of loadings, okay, in our AML matrix, as we did in the Areal matrix. So now we are going to do the same in our AML matrix also. So this 15 kip is coming from this reaction, this 15 kip. This 15 kip is coming from this here, this 5 kip. And all these are positive. Why positive? Because they are exactly in the same direction as in our assumed direction, as the assumed direction of our AM1, AM2 up to AM7. Okay, so now if the fixed end action is exactly in the same direction of your chosen direction of these AM values, so you will be taking it as positive. Else you will be taking them negative. Okay, so I hope you are getting this, and we did explain this in the last problem also. Now let's go through this. This 37.5, this is corresponding to our AML5. Now our AML5 is positive clockwise, but this is anti-clockwise. We have taken this as negative, and this value is corresponding to our AML6. Now this is clockwise. This is also clockwise, so this is taken as positive. Now this corresponds to AML7. Now this is anti-clockwise, but the assumed direction of our AML7 is clockwise. So we will be taking it as negative 25. Now I have put the question marks here. So why there are question marks? Because now these values we will be finding in the next steps. Okay, so now let's find them. Okay, now in this step, now we have applied this 0.002 radians rotation clockwise. Now these are the induced moments. Okay, and we did explain this in the step number 2. Okay, now we need to now write the values corresponding to our AML1, AML2, AML3. So now this negative 8.88 is coming from where? It is coming from this reaction. Why negative? Because now it is downward, and the assumed direction of our AM1 is upward. So as it is downward, so it will be taken as negative. Similarly, this is 8.88, this value. Why this is 0? Because just to the right of this support there is no reaction, so 0, and at this end also there is no reaction, so it is also 0. Now we come to the moments. So now the moment induced here is 88.88, and it is clockwise, so we take it as positive. And also the moment at this end is positive because it is clockwise. And why this value is 0? Because just to the right of this support there is no moment induced by this 0.002 clockwise rotation. That's why we will be taking this as 0. Now we are left with the only one question mark in this matrix, which we need to find in this step. So here we have we need to find out the fixed end actions due to this 1-inch settlement. So now this 49.18 value is coming from where? It is coming from this one. Okay, both are the same thing actually. This negative 49.8. Why? Because this is downward, and the assumed direction of our AM2 is upward. This is also downward, so it will be taken as negative. And similarly, you have to pick all these values. This is the AML4, this is the AML5, this is the AML6, this is the AML7. Okay, so now we need to sum them up, and when we sum them, keeping their sign in mind, we get these values as our final AML1, AML2, AML3, AML4, AML5, AML6, and AML7 values. Okay. So now this becomes our AML matrix. This one. Now we need to find the AMD matrix. AMD matrix. There is no changes in the AMD matrix. It is exactly as we did in the previous problem. So what you need to do, you need to find out these fixed inductions values corresponding to your AM1 up to AM7, and these values should come from, first they should come from unit rotation 8 coordinate 1, and then unit rotation 8 coordinate 2. Now this becomes our AMD matrix. Okay. What is AMD11? AMD11 means that the value of the fixed induction 8 or corresponding to AM1 location. Now this one is not showing these coordinates 1 or 2. No, it is not showing these 1 or 2. This first value, it is actually showing the location of your first member induction. So our AM1 is, if you remember, our AM1 value was here, AM2 was here, AM3 was here. So now this first, all these values, they're just showing the location of your member inductions. This is the AM1. Now the second value is showing now the location at which the unit displacement is applied. We know now that the unit displacement is applied here at coordinate 2. Okay, on the previous slide, unit rotation is applied at the coordinate 1. That's why there is 1 repeated throughout this column. Okay, because we are finding the values of the member inductions or the fixed inductions which are coming from the unit rotation at coordinate 1, and that's why we have two repeated in this second matrix, because here the unit rotation is applied at the coordinate number 2. So it should be now very clear to you that the first value, this first value, it is showing the location of the member induction, and the second value is showing the coordinates which we assigned to our specified displacements. Okay, so now these are the values of the AMD matrix. I'll put the values of these matrices here in this equation. This is the AML matrix, this is the EI value, this is the AMD matrix, and this is the D matrix. Okay, if you remember, in this first part of this problem, we calculated this matrix. Now when you solve these matrices, you get these values as the member inductions. Okay, so is to now you need to draw the shear force and bending moment diagram. So you quickly draw this shear force and bending moment diagram for this problem. This is your class activity. And after that, I will go to the next problem. Okay, now let's have a look at this problem number 3 on this stiffness method. Now, what we have here in this problem, we have this 1 kip per foot uniformly distributed load over this entire span. Okay, and then we have an internal hinge here, and this internal hinge is at 10 feet from this support A and at 20 feet from this support B. So Now, how we will now be incorporating this internal hinge in our structure, and how we will now be finding the values of matrices in different steps. Now let's have a look at this. We are asked to analyze this beam using the stiffness method. The EI value is constant for this beam. Now, the first question which arises in the mind is the what should be the kinematic indeterminacy. As we know that we have fixed ends here at A and B. These are fixed supports, so there is no rotation or there is no displacement possible at these supports. But when the load is applied, this point where we have internal hinge, this will translate downward. Also, here we will have rotation, and also here we will have rotation. Now, these two rotation values, they are not the same, they are not equal. Why not equal? Because this internal hinge, it is not at the middle of the span. We can see that it is 20 feet from one support, 10 feet from the other support. So if this internal hinge was at the middle, which means that 15 feet from this support, 15 feet from this support, then the value of θ1 would have been equal to the value of θ2. But in this case, these values are not the same. So the kinematic indeterminacy is 3 degrees, and which are θ1, θ2, and the this translation, and all these displacements are due to this internal hinge. Okay, all these values are due to this internal hinge. So now let's see how we do this. Now in this step we are going to specify these displacements. So now we know that we have this d1. D1 is actually a rotation. So we have shown this by this clockwise one. This d2 is also a rotation. We have shown this by this d2, and d3 is a translation, downward translation. So we have shown this by the d3. So these are the values of d1, d2, and d3. Now we need to find these values of d1, d2, and d3 because these values are unknown. What are the values of AD1, AD2, and AD3? Now corresponding to your d1, is there any external action applied? No, there is no external action applied here. So the AD1 value is 0. Is there any external action acting corresponding to this D2? No, there is no this external action. So this value is 0. Is there any vertically applied external action corresponding to this D3? No. For example, if there was this vertical, this load, external load of 10 kip, let's say, at this joint, this internal hinge, so then this value would be our AD3 value. But as in this structure, we don't have any such external action, so this value is also 0. Now, all the things will remain the same as we did in the previous problems for D1 and D2. Only changes will be in this D3. So now you need to look at how I do this. First, we need to now restrain all these displacements. So now we should replace the hinge by this fixed end. Now, when I replace this by a fixed support, so now all the displacements, now they are equal to 0. In other words, they are restrained. Now the Areal matrix, exactly the same. What is the Areal matrix? It is coming from the fixed end actions corresponding to our specified displacements of d1, d2, and d3. And these fixed end actions are coming from the external load when applied on our restraint structure. This is our restraint structure. So now, if you remember, at location 1, we have our d1 acting clockwise. At location 2, we have our d2 acting clockwise. And exactly at the same support, we have our d3, which is acting downward. We have supposed our d3 to be directed downward. So now, corresponding to this d1, d2, and d3, now we need to pick the values. So now, how these friction actions are coming? Now you know that from the previous problem. We already did that. WL square over 12, and you know that this is WL over 2. So this value of 12.5 kip fit, now this will be taken corresponding to our d1. So this becomes our ADL1 value. Similarly, this 50 kip fit value, this is anti-clockwise. Our assumed direction of d2 was clockwise. Now this will be negative 50. And the assumed direction of our d3 is downward, but here the value, this one is upward, this one is upward. So now when we add them, this becomes 22.5, but negative, because these are in opposite direction to our assumed direction of our d3. So now, as I already told you, that you need to pick the values of the fixed end actions corresponding to your specified displacements. So here we need now to choose the values of the vertical reactions. These vertical reactions is ADL3. Why? Because they are corresponding to D3. Okay, I hope this is clear. So now we need to find out the values of the stiffness matrix. What we need to do now, we need to give a clockwise rotation at coordinate 1, and due to this clockwise rotation, this one, it will induce moments at the near end and the far end. Similarly, these are the balancing the reactions. Now, as we have chosen separate D1 and D2 at this support, okay, so now if we rotate corresponding to D1, so it will have no effect on the other side of the this fixed support, because when we rotate D1, at the same time the other values remain unchanged. So if you are rotating this D1 to D2 and D3, they remain fixed. They remain 0. So if this is rotating, so it will have only the effect induced moments in this span, and it will have no induced moments in this span, because this is already a fixed ended span. So these moments will not be transferred in this span. Okay, so now corresponding to these moments, now we have these external reactions, and now what is the value of S11? It is the value at 1 due to rotation applied at 1. So now this is this value. Similarly, S21 value is the moment at 2 due to this rotation at 1. So as we can see that there is no induced moment here, so it is 0. Similarly, S31, which is this vertical reaction, so there is a vertical reaction, which is this one, and it is upward, so this will be taken as negative. Similarly, now you need to rotate this corresponding to your D2, and it will have no induced moments in this span. So now your S12 value will be 0, and your S22 value now will be equal to 0.2 EI. Why? Because this is the induced moment. Why this is 0? Because there is no induced moment corresponding to coordinate 1. And why this is 0.015 EI? Because this is a vertical reaction which is caused by this unit rotation. Now you need to apply the unit value, unit displacement, D3. So when you give a displacement to this support downward by an amount of 1 inch, and the values of this, now this is exactly the same as we did in this problem number 2, where the support was settling down by 1 inch. 6 times EI divided by L square. This is 6 EI divided by L square. And the corresponding reactions, they will be equal to 12 EI divided by L cube. Okay, and 12 EI times this unit translation. So as this translation is equal to 1, so you get these values to be equal to 12 EI over L cube and 6 EI over L square. Similarly, you now need to pick the values of S13 here. A1 due to displacement at3. So this is 1. This is the induced moment at 1. This is 0.06 EI. This is why this is negative. 0.06 times EI. Why this is negative? Because this is anti-clockwise, and our assumed direction of D1 is clockwise. Okay. Similarly, you pick the values of S23 and this is S33. So why S33? Because this is at3 due to displacement applied at 3. So these values, if you sum them, so you get this value as S33. So now this becomes your stiffness matrix. Now you put these values in this equation, so you get these values of D1, D2, and D3 with 1 over EI is common. Now what you need to do, you need to select your AM1 values, AM2, AM3, AM4, AM5, and up to AM6. Now corresponding to these values, now you pick the values of AML1, AML2, AML3. Now you know this, okay, from where these values are coming. You have applied this load on your restrained structure, and you are finding these friction reactions corresponding to your AM1, AM2 up to AM6 values. This becomes our AML matrix. Now you need to find the AMD matrix. So exactly as we did for the stiffness matrix, now we will be finding the values of the AMD matrix. So now this becomes our AMD matrix. Okay, this becomes our AMD matrix. Again, I don't need to go in detail here because we have already did it quite many times. Now this, you can see that this second value, this is fixed in this column, and it is 1. This is 2. This is 3. So these are showing the coordinates of your specified displacements. The second value. Okay, the second value. This one. These are corresponding to your specified displacement. These are the coordinates of specified displacements. And what are these first values corresponding to? This first value, this is the location of your AM, member end action. So this 1 is the member end action 1, this is member end action 2, this is member end action 3. So I hope this is now more clear to you. So this becomes our AMD matrix. Now you need to solve these matrices, and when you solve them, you get these values of your member end actions. Now these are your member end actions, and you draw the shear force and bending moment diagram. So this becomes your shear force and bending moment diagram for this structure. So that's all for this lecture number 5. Now if you have any question, you can now start asking, and I will be now clearing one by one. I will be answering one by one. Okay.